Welcome back to Calculus 2. This is the second part of our three-part series on partial fraction decomposition. So let's pick up exactly where part 1 ended. We were covering the first case for partial fraction decomposition, distinct linear factors. Let's get to a second example, example 2. All right, now hopefully you're just continuing directly after part 1 ended. I'm going to assume so. So let me give you time to attempt this. This one is very similar to our first example. Pause the video and give yourself several minutes to attempt this. I'll keep the steps on the screen here. All right, let's start going through the steps. Arguably the most important one to get right from the beginning is to completely factor the denominator. Now, before we do so, before we get to the algebra, always check that your rational function is proper. So in other words, that the degree of the polynomial in the denominator is strictly bigger than that in the numerator. And here we have a degree 3 polynomial in the denominator, but a degree 2 polynomial in the numerator. This rational function that we're integrating is proper. If your rational function is improper, you need to perform long division first. But this one being proper, we don't have to. Okay, so let's go ahead and get to factoring the denominator. This one might be a little tricky, hence why we started this lecture series, is three parts, by making you aware most of the difficulties are algebraic in nature, not at the level of calculus. Here, the tricky part is probably just factoring this. For terms, we can use factoring by grouping. Group the first two terms, factor out the greatest common factor, x squared. Group the last two terms, factor out a greatest common factor of -1. And then from that resulting expression, we can factor out x plus 2 from both terms remaining. We get the factor x squared minus 1, which can be further factored as a difference of squares. So we get our complete factorization as x plus 2 times x plus 1 times x minus 1. Make sure you're comfortable with that. That is one aspect of what makes partial fraction decomposition complicated, factoring problems like this. All right, now with your denominator factored, we can advance to the partial fraction decomposition. Always rewrite your rational expression, your rational function, with the factored denominator. And since we have 3 distinct different linear factors in your denominator, we get 3 partial fractions. Each fraction is of the form some unknown constant divided by the linear factor. So we have 3 linear factors, we get 3 partial fractions with constants a, b, and c in their numerators. All right, this is another part to get correct. Make sure you're able to get the correct partial fraction decomposition. If it's wrong from the beginning, it's going to throw everything off. All right, at any point, if it seems like I'm taking a long pause, that's just to give you time to maybe verify. So even if I don't say to pause the video, if I do a long dramatic pause, you feel free to pause the video to confirm algebraic results. That's a long dramatic pause. Let's get to the next part of how we're going to solve for the values of a, b, and c. Now, we're always going to try to eliminate fractions from this equation, this identity. We're going to look at it as the middle part, that left side, with the factored denominator. And on the right side of that identity or equation, we have the 3 partial fractions. How we eliminate fractions is multiplying both sides by the least common denominator. The LCD here is x plus 2 times x plus 1 times x minus 1. So let's multiply both sides of that equation, that identity, by that. And that should cancel all the factors in every fraction. Again, long dramatic pause in case you wanted to pause. So go ahead and distribute that LCD through the brackets to each of the three fractions. And notice on the left side that that LCD completely cancels the denominator. All right, so I'm going to pause just to make sure you're comfortable distributing and canceling things out. Your end result should contain no fractions. There should be no factors left in your denominators anywhere. All right, so let's advance. This should be your end result by eliminating fractions, multiplying both sides by the LCD. The nice thing about the case of distinct linear factors, linear equations always have a solution. We can choose x values one at a time that make each linear factor become 0. So we're going to plug in values for x. You can probably see the values of x we're going to plug in: -1, 1, and -2. Those are the three values of x that make individually each of those factors evaluate to 0. So let's take that one at a time. We're going to plug in x equals -1, and we'll be able to solve for an equation for one of the unknowns. We'll plug in x equals 1. That'll give us an equation to solve for another of the unknowns. And then we'll finally plug in x equals -2, giving us a third equation to solve for the third unknown. All right, so we're picking three values because we have three unknowns. Three unknowns requires three equations. The case of distinct linear factors, plugging in is incredibly efficient. When we get to part 2 in a little bit in this lecture, the case of repeated linear factors, we'll have an alternate method for solving for the constants besides plugging in. All right, so here, pause, plug in those three values of x, -1, 1, and -2. You should be able to very quickly solve for the values of a, b, and c. All right, so let's go through that. If you plug in x equals -1 on both sides, notice there are x's now from the numerator of your original fraction. We have x's on the left. We have to plug in -1 on that left side. Plugging in -1 to 2x squared minus x minus 7. If you're careful, you should get the equation -4 equals -2b. Divide by -2, you get that b comes out to have the value 2. All right, we're going to individually plug in x equals 1 to both sides. You should get this equation, -6 equals 6c. Divide that equation by 6, you get c equals -1. And then finally, to solve for our third unknown, a, we have currently the values of b and c. Plug in x equals -2 to both sides, and you should be left with only a. The equation you have is 3 equals 3a. Divide by 3, you get a equals 1. Okay, so for the case of distinct linear factors, solving for even 20 unknowns really quick. All right, we're going to plug these values back into our partial fraction decomposition, since we have the values of a, b, and c. That's our partial fraction decomposition kind of above at the top of the page. And here, since we have linear factors, they're all going to integrate to natural logs. So we're pretty much done. The algebra is more involved than the calculus. Integrate each of those three partial fractions, and we get 3 natural logs. And there is our antiderivative, our answer for this integral. Okay, now that was pretty simple. The first case of distinct linear factors is by far the simplest. From here on out, each different case of repeated linear factors, and then getting into parts 3 and 4 on irreducible quadratic factors, those cases are where the algebra becomes quite involved and rather lengthy. So that's it for part 1, case 1 of distinct linear factors. Let's get to case 2, repeated linear factors. All right, so what I want to start with is we have a rational function, p of x divided by q of x. We're going to reserve q of x to denote the denominator or the polynomial in the denominator. And we have examples here of, I'll say, two standard factorizations with repeated factors. All right, so let's take a look at the factors in example 1. Now, I want you to identify your factors as x plus 2 and x plus 1. It is correct to say x plus 1 squared is a factor because it appears in the factorization, but we're going to think of that exponent 2 as telling us how many times that factor is repeated. And that plays into the partial fraction decomposition in this case. So identify, for example 1 here, the factors as x plus 2 and x plus 1. X plus 1 is a repeated factor. It's repeated twice. What I have on the right there is if you were to multiply that out, just in case you want to work backwards from the right to the left, what the kind of multiplied out expanded version is, in case you want to try to refactor that. All right, example 2 contains 2 repeated factors. Your factors are x, x minus 3, and x minus 1. The exponents on x squared and x minus 1 cubed, the 2 and the 3, tell you individually how many of those times are repeated. So x is repeated twice, and x minus 1 is repeated 3 times. Thrice, if you want to be fancy. All right, and again, if you're up for the challenge of factoring, give it a try, multiply that out, and try to refactor that. If you can, your algebra skills are top notch. All right, now there is a modification to the partial fraction decomposition in this case when you have a repeated linear factor. Now I'm going to write down the standard mathematical notation. I realize it will probably not make sense to many students in our course, Calculus 2. The examples we'll be getting to are where I find students really get what the partial fraction decomposition is. But since many of you are continuing beyond the calculus sequence, let's write down the standard mathematical notation. All right, so we're going to focus on first having the denominator completely factored. The denominator, we're denoting it as q of x. And let's suppose that q of x, somewhere in the factorization, we have a linear factor of the form ax plus b, but in the factorization, there is ax plus b to a power. Here we're writing it as the nth power. So we're going to say the linear factor ax plus b, writing it here, is repeated n times. All right, now this is just one of possibly many factors in your denominator. We're going to combine this with case 1 in some examples momentarily. But if we just focus on this repeated linear factor, our partial fractions become the following. Ideally, the repeated power is small. How we proceed, and this is again beyond the scope of the course for proving why partial fraction decomposition works. Here we just typically implement it, saving proofs for later after the calculus sequence. The way we write down the partial fractions is we start with the basic idea from case 1, a constant over the linear factor. The linear factor being ax plus b. How we account for the repeated nature of this factor, ax plus b to the nth power, is we start with the denominator as ax plus b to the first power, and then we increase that exponent on the factor 1 power at a time, going from ax plus b to the first power. The second partial fraction has ax plus b squared in the denominator, and then it would be ax plus b cubed, ax plus b to the fourth, adding additional partial fractions until you reach however many times that factor is repeated, n, written here in this factorization. All right, now if the exponent on that repeated factor is very large, you get a large amount of partial fractions. Typically, for most problems, the exponent on a repeated factor will be 2 or 3. All right, I realize this probably won't make much sense, but let's take a look at some specific examples. All right, we're going to combine this with case 1. We're going to kind of assume that you're okay with case 1, distinct linear factors. So pause the video and give yourself an attempt at writing out this rational function's partial fraction decomposition. We'll check in about a minute. All right, now here we're just writing out the partial fraction decomposition. We're not going to worry about solving for any of the values A, B, C, D, however many we have. Not in this example. All right, now notice here before I advance, you have two factors, the linear factors being x plus 2 and x plus 1. X plus 1 is a repeated factor. It's repeated twice. So our decomposition, we use the decomposition for linear factors, a constant over the factor, a over x plus 2, and then b over x plus 1. Since x plus 1 is a repeated factor, we include another partial fraction with the denominator x plus 1 squared. And we don't have to continue beyond that because the repeated factor x plus 1 was only repeated twice. All right, so now it's probably starting to sink in. Let's take a look at a second example just on writing out the partial fraction decomposition. Don't worry about solving for the values of the constants. All right, pause the video and give this one a try. All right, this one is very similar. Make sure you always first identify your linear factors. Your linear factors are 2x minus 1, which is repeated twice. The other linear factor is x minus 1. All right, since 2x minus 1 was repeated twice, that factor gives us two partial fractions. The factor of x minus 1 just gives us a single partial fraction. All right, now it's probably starting to sink in. Let's take a look at a third one. This would probably not be a good like full-on integral calculus 2 question. You might see why, but at least we can use this to write out a partial fraction decomposition in a very complicated case. So pause the video and just write out the partial fraction decomposition. All right, now this one's a little tricky. It involves several repeated factors, all of which of the factors are linear. First, identify your linear factors, no exponents. Your linear factors are x, x minus 3, and x minus 1. Now, the factor of x is repeated twice. That'll give you two partial fractions. The factor x minus 3 is not repeated. That'll give you one partial fraction. And then the factor x minus 1 is repeated 3 times. That will give you 3 partial fractions. If we do that in total, well, we get a lot of partial fractions. 2 from the first repeated factor, 1 from the middle factor of x minus 3, and then 3 more partial fractions from the third factor, x minus 1, which is repeated 3 times. Now, the reason why I said this is not a good calculus problem is it's going to require you to solve for 6 unknowns. And in my opinion, there's really nothing learned or demonstrated to me on my end with your understanding being able to solve, let's say, 3 or 4 unknowns versus 6 here. So typical, I'll say, quiz and exam questions, at most, probably 4 unknowns to solve for. This one could be an exam question if some of the values work out nicely, but in general, 6 unknowns or more is a little too lengthy, in my opinion, for a calculus question on an exam. Okay, now these are just the algebraic steps of writing out the partial fraction decomposition. For all of these 3 examples, the right-hand sides with the partial fractions, we would then take the next step of integrating them. And you can probably see some of the different integrals you'll get, natural logs, you'll get some powers, and we'll see what else. All right, now let's get to a next example where we're going to take a look at a second way to solve for the unknowns. As soon as we start case 2 of repeated linear factors, the algebra kind of increases greatly. So it's still moderate, still doable here in case 2, repeated linear factors. Parts 3 and 4 dealing with irreducible quadratic factors, the algebra becomes nightmarish. It's awful, but we're not there yet. Calm before the storm. All right, now we currently have one method to solve for the unknowns, which we used in case 1, plugging in. Since we have linear factors still, some of them which may be repeated, we can still use the plugging in approach. Linear equations always have a solution. So if we have a factor ax plus b, we would want to plug in negative b over a. That would cancel it out and give you that expression, that linear factor becoming 0. The second approach, which we haven't gone through yet, which we're going to introduce in the next example, example 3, that will be where we take a look at an alternate method called equating coefficients. Example 3, we're going to solve for the unknowns in 2 ways, so you can kind of see maybe for you individually what might be easier or harder. All right, so let's advance to example 3. I'd like you to make an attempt at this. I feel somewhat confident that you're starting to incorporate what we've been covering in the first part, and you're starting to absorb the content. So pause the video and give yourself several minutes to see if you can complete this problem fully. We'll check in a few minutes. All right, welcome back. Here, the first step is already done for us. So the math gods have smiled upon us. They gave us an example where the denominator is already factored. All right, so we can skip that. We can go straight to the partial fraction decomposition. We have factors 2x minus 1 and x minus 1. 2x minus 1 is repeated twice, so we get 2 partial fractions from that single repeated linear factor. All right, this one is not too bad. We have 3 unknowns to solve for, A, B, and C. Again, long dramatic pause in case you wanted to pause. All right, let's advance. This will be where we get into 2 different ways to solve for the unknowns. So make sure you copy this down, so pause the video if needed. And we're going to look at 2 different ways to solve for the constants A, B, and C. Let's get to the first way. The first way is our plugging in approach. Now, again, I'd like you to try this. This is actually probably the more efficient way for this example. Eliminate fractions first, multiply both sides by the LCD. Pause the video and see if you can solve for A, B, and C by plugging in. Here, there's a problem. There's 2 good values for x to pick. Choose a third value of x, any value, to solve for a third unknown constant here. We'll check in a few minutes. All right, now there should be 2 easy value of x to come up with. What makes 2x minus 1 equal to 0? X equals a half. What makes x minus 1 equal to 0? X equals 1. So we have 2 nice values, simple values to plug in, 1 and 1/2. You should very quickly be able to solve for C and B. But here, since 2x minus 1 was repeated, we don't have a third distinct linear factor to solve here for A. Now what we can do, viewing this as an identity, is plug in any other value for x. So just pick any number besides 1.5. As long as it's a number, it will work. Now, generally, we try to use 0 or small positive integer values. Here, let's plug in x equals 0. Again, you could choose any value for x, but 0 is a nice value. So pause the video here and see where this leads you. Make sure to plug that in also on the left side. All right, now the equation you should get might have a, b, and c in it, but we already know the values of b and c. So your first step in plugging in x equals 0, you should get this equation. It contains all 3 unknowns, but realize at this point in solving this problem, we know the values of b and c. If you plug in b as 3 and c as -1, you'll have an equation only involving a, which is your last unknown constant to solve for. So plug in b equals 3, c equals -1, simplify, subtract, add. You should get this equation, which will very quickly solve to give you, long dramatic pause, a equals 2. Okay, so we have all 3 of our values. We have a, b, and c. We now have basically the partial fraction completely determined, the partial fraction decomposition, that is. All right, now I want to take a look at the second new approach called equating coefficients, and we should get the same 3 values. A should be 2, B should be 3, and C should be -1. I will say, for this example, example 3, the plugging in approach, algebraically, is probably simplest. You'll probably see why in a moment, but realize when we get to case 3 and case 4 involving irreducible quadratic factors, the new approach, which we're about to get to, is probably more efficient. All right, so let's advance to the second new way to do this, which is equating coefficients. All right, so the first part about eliminating fractions is exactly the same. That's present in both methods. We want to get rid of fractions so that way it's easy to go from there. Now, what we're not going to do is plug in values for x. That's the first approach. Now, this one is still algebraically tedious because we're going to start, for this method called equating coefficients, we're going to start by fully multiplying out, expanding, foiling that right-hand side. Now, I realize this could be quite involved, so pause the video and give yourself enough time to fully multiply out that right-hand side. In the lecture, it will look like a few seconds because I'm intending for you to pause and attempt that. That's going to take you a little bit of time, so this new approach is probably not any more efficient for this example, example 3. So pause the video, multiply out that right-hand side. All right, it's really tedious. I'm not claiming it's any simpler than the plugging in approach. This is just an alternate method. Now, what I'd like you to do is take a look at your end result before we advance in the lecture here. With whatever you have for your end result from fully multiplying out, you should see there's some like terms. There's like powers of x. You should have x squareds all over the place, some terms involving x, and then some numbers by themselves with no x on them, constants. Now we're going to collect like terms together. And what we should get is kind of an end result. I have at the top there, just for reference, the same values for A, B, and C. All right, so I'll keep that on the screen just as a kind of a check to see where we're going. That was from our plugging in approach. If you collect like terms, you should get this result. This is just collecting all the like terms of x squared, x, and constants on that fully expanded, multiplied out right-hand side. All right, so add the coefficients of x squared add those of x, and then collect your constant terms at the end, those without x on them. All right, and this is where it gets a little tricky. Now, the name equating coefficients is going to view this equation as an identity. We have a degree 2 polynomial on the right side. We have x squared, x, and constants, but it looks like we have a degree 1 polynomial on the left side, x minus 2. Now, equating coefficients, the name comes from, we take a look at each like term on both sides and then equate the coefficient in front of them on both sides. Now, you might be thinking, wait a second, there's an x squared on the right side. There is no x squared term on the left side. Well, we cheat. There is an x squared term, just that its coefficient is 0. So let me put 0x squared on that left side. Now we have x squareds on both sides, we have x's on both sides, and constants. How we get our 3 equations, remember we have 3 unknowns we're solving for. We need 3 equations. We're going to equate the coefficients for each power of x, or like term, on each side. Let's take this one coefficient at a time, or one like term. We'll go down in order, starting with x squared. All right, if we take a look at the coefficients of the x squared term on both sides, on the left, the coefficient of x squared is 0, since there was no x squared initially, so we think of it as being 0x squared. Now, the coefficient of x squared on your right side is 2a plus 4c. So our x squared comparison for the coefficients, the equating of the coefficients of x squared, gives you the equation 0 equals 2a plus 4c. All right, that's one of 3 equations we're going to need. Next, we're going to equate coefficients of x on both sides. On the left, x has a coefficient of 1. On the right side, x has a coefficient of negative 3a plus b minus 4c. So we get our second equation, equating the coefficients of x on both sides, 1 on the left, and then negative 3a plus b minus 4c on the right. Your last equation is equating the constant terms on both sides. On the left, we have a constant, negative 2. On the right, we have 3 of them, but they're all combined constants. This all combines to give a constant. The constant on the right side is a minus b plus c, the part or term without a power of x on it. So our third and final equation is negative 2 equals a minus b plus c. All 3 equations came by equating coefficients of the 3 like terms, x squared, x, and the constants on both sides. Now, pause the video, make sure you thoroughly understand where these 3 equations come from. For this example, example 3, this is definitely not the most efficient method. When we get to case 3 and case 4, involving irreducible quadratic factors, equating coefficients like we're going through here, this approach for solving for the constants is usually more efficient. All right, so what we have to do now is solve this system of 3 equations for 3 unknowns. And again, this is all the kind of complicated algebra I was making you aware of at the start of the first part. All right, now there's really no rules for solving a system of equations, but we're going to try to notice kind of some simpler equations here. Notice the first equation, we can easily solve it for a. So we're going to use the substitution approach, solve for your one of equation for one unknown, and then substitute or plug it in to the others. So let's solve 0 equals 2a plus 4c for a. That'll give you a equals negative 2c. What we can now do is take that and substitute it into the second and third equations, algebraically replace all a's in those equations with negative 2c. Pause, give yourself some time to work that out, plug that into your x equation, and then the constant equation, the second and third equations there. Okay? You should arrive simplifying at these equations. Notice now what we're left with are two equations only involving the unknowns c and b. So right now, within this larger system of equations, we're solving a system of two equations for the two unknowns c and b. Now, these two equations are set up nicely that we can use elimination. Notice, if I add those equations together, a variable eliminates or cancels. Add these equations and the b's cancel. And you should get an equation only involving c, which you can solve to get c equals -1. If you take c equals -1 and plug it into either of those two equations, you should get b equals 3. Now, since you have the value of c and b, you can back substitute in any previous equation to get the last value, the value for a. And we're going to go to our first equation we got, a equals -2c, and we'll plug in c equals -1. And if you plug in c is -1 to that, you should get a as +2. Confirming the same three values that we get from the plugging in approach. All right, again, for example 3 here, plugging in is probably more efficient and easier for you. The equating coefficients method here definitely probably is more complicated. But for parts or cases 3 and 4, equating coefficients is probably more efficient. All right, let's advance back to the calculus problem. So we kind of are advancing through the problem. We did the partial fraction decomposition. We just solved for the unknowns. Now we can advance to integrating. All right, so let's go back to the kind of first page. We're going to plug in our values for a, b, and c. And we now have rewritten our original rational function as 3 separate, simpler rational functions, the partial fractions, which can easily be integrated. Now, again, the algebra is the more detailed and complicated part here. The integrating is probably the simplest part. All right, and as it turns out, that first fraction can be integrated with the substitution u equals 2x minus 1. You can also use the 1/a shortcut if you recognize that as being a term in the denominator, ax plus b. You have basically 1 over a variable that'll integrate to a natural log. The second partial fraction, 3 divided by 2x minus 1 squared, that doesn't integrate to a natural log, but you can use the u substitution and then apply the power rule for antiderivatives. Use the substitution for the second integral as u equals 2x minus 1. And then the third fraction, 1 over x minus 1, that integrates to a straightforward natural log. All right, so make sure you're comfortable with the end step involving calculus here, evaluating the antiderivatives. Most of the work for this problem was in probably doing the partial fraction decomposition. Make sure you're comfortable where the 1/2 factors come from and -1/2. And if we clean up our example, just cancel some factors out, we get this lovely end result for our integral. All right, that concludes part 2 of our lecture series, dealing with covering distinct linear factors and now repeated linear factors. Part 3, which we'll pick up with right after this, will introduce everything related to irreducible quadratic factors.